So here we're just doing a really simple example.
This I understood.
This you understand, all right? And so you're right. Now that you mention it, I have never made slides to explain this. So that is a problem. And I'm not really good at making pictures and writing with my my tablet here. Draw. What was the thing? I was using something. Was it Draw?
Draw.io.
Paint. Paint. That was what it was here. All right. Maybe someday I should make slides about this. All right. So let's close. What are you doing? You going away?
Just click outside.
Oh, there we go. Everybody see this?
Yeah.
All right. So what are we doing?
Yeah.
Let's see if we can draw. Yeah, we have, let's say we have some axes here, and we have some function that grows, right? And our goal, and it's and it happens to be discrete, right? So go back to black here, right? There's a value for here, and oh, that's still blue. Not that it really matters, right? There's these various values, right? So we want to add up this amount plus this amount, right? Plus this amount, all the way up to this amount, right? Everybody got? And why are we doing this? Well, maybe there's a loop, and the loop takes. There's my mouse. My loop takes. Can you see my mouse move?
Yeah.
I know there's often a delay between when I move it and when you move it. Like I say, move, and then does it take a while? Anyway.
Yeah, there's a delay.
There's a delay, so I try not to move my mouse too fast. But right, the first bar tells me how long the first iteration takes, right? And the second bar tells me how long the second iteration takes, right? And then obviously this last bar tells me how long the last iteration takes, right? And I want to add them up. And one way to approximate that is you turn it from discrete to a curve, right? And then you could integrate under the curve, right? But I don't think that's a very satisfying answer, because you don't really know how to add things. But, you know, the truth is it's been a while since you've taken calculus, and you might not know how to integrate either, all right? So the other thing, if you look at Corman or you look at what other people teach, they may have a long discussion about how to add perfectly, right? So if you go back here, in this example, right, 1 plus 2 plus 3 plus 4 adds up to n times n plus 1 divided by 2, right? And do I really care about that plus 1?
No.
No. In fact, do I care about the divide by 2?
Nope.
No, right? Because, right, we've already just been, I haven't actually, but, we've tried to teach you big O notation, right? So the big O notation says, ignore those small terms, ignore the multiplicative constant, and think about this as n squared, right?
Mm-hmm.
So if we go back to our drawing, in the example we just did, it's a line, right? But now we're trying to say, hey, we could have much more complicated curves, right? Let's say that this here is an arbitrary function. So for value, if this value I here, I, then the height is f of I, right? Everybody get that?
Yeah.
So we need to approximate this shape. And we need to approximate it. It'd be nice to have a lower bound and an upper bound that's within a constant of each other. So the upper bound is, let's just draw a line directly across. And then I'll say my sum is of f, right, is less than or equal to n times f of n, right?
Yep.
Why is that? Well, what's the area of this box? Well, we're summing from 1 to n. So the number of items that we're summing is n, and each item is less than the bit. Here I'm also assuming, when I say f of n here, I mean the biggest, right? This is the biggest, right? So that honestly, sometimes this biggest is f of 1, right? Why would it be a f of 1? Is, well, when the curve decreases, right? So when the curve decreases, then what I mean by here, it's n times the biggest number, right? If I wince, it's because I got the worst cramps today. I don't know why. I haven't had cramps like this since I had a kidney stone. I hope I don't have one of those again. All right, so now we want a lower bound, right? So what we're going to do is we're going to cut just a simple bound. We're going to cut the thing in half, right? So this is n over 2, right? And we're going to take this box here, right? So proof by picture, you can see that the area of this box is less than the area of under the entire curve. Why? Because we're ignoring the first half, and that makes it all makes our area smaller. And for the second half, we're going to assume that the smallest, since we're assuming f is increasing, then our smallest is f of n over 2. So here we're going to say that this is less than or equal to n over 2 times f
Of n over 2.
of n over 2, right?
Yep.
All right, so now those are our two bounds, and we want to know, are those bounds, are they within a big O, a constant multiplicative constant of each other? Well, this 2 here doesn't matter, right? But what about the 2 inside of the f, right? It depends on what f is, right? So suppose f equals n to the d, right? So if we divide by n over 2 all to the d, right? Why am I doing that? Well, this is f of n, which is n to the d, and this over here is n over 2 to the d, right? And if I want to know the ratio between them, I divide through, right? And what does this give me? This gives me, move your guys' faces, 2
Constant.
to the d, right? Which, though is big, is still a constant,
Yeah.
right? So let's go back to our slide here. What are we doing here? Oh, this thing is in the way again. right? So what are we saying here is, suppose we have some function, f of n, and we want to add them up, right? Here we want to know what is f of 1 plus f of 2 plus f of 3. Well, the one example that we gave in class is our f is just linear, right? F, here we're adding up 1 plus 2 plus 3, and that's big O of n squared, right? And so here I'm
Isn't that
saying,
theta though?
what? Theta.
Isn't that theta?
Yeah, theta big O. One is, you know the difference? One says I have an upper bound, and the other one says I have an upper bound and a lower bound. So, yeah. Usually I'm talking about algorithms, so I focus on the big O. But you're absolutely right, it's theta. All right? So here's a general possible rule, right? Remember, here's a possible answer, is you take the number of terms times the biggest term, right? And call that your answer. And when is that good enough? Well, here, if f is into the d, right? I to the d, then the answer is good enough. And in fact, you might remember from integrating that if you want to integrate I to the d, well, you get 1 over d times I to the d plus 1, right? So there's a 1 over d here. Does that make sense?
Yeah.
Now, what about these other examples? Well, if we go back to our paint, it's possible that, here, let's try can we scroll down here? What happens if my function grows really, really fast, right? Then the sum over the curve, right? This is like an exponential curve, right? It's dominated by, the sum is dominated by the last term, right? So here, if you're adding up, what's 1 plus 2 plus 4 plus 8, so forth, right? We're going to do that example later. But you might know that it adds up to double the last number minus 1, right?
Mm-hmm.
So the last number is 2 to the n. So it's dominated, it's within a constant of the last number, right? And this is just saying, as long as you're summing up anything that's an exponential, then it's dominated by the last thing, right? And everybody follow that example?
Yeah.
It's
So-
kind of hard to follow this.
Yeah, for sure.
And sometimes you draw is just a little hard to imagine.
Yeah, I know it. My pictures aren't very good.
And I saw the drawing doesn't look, I mean,
I think I might have slides on these somewhere. I should find them. My point was that you didn't have to do very much right here, right? And my point is all that you really needed to know for this example was this, right?
yeah.
And we're going to come back to these things periodically. And so my intention at this point in the slides was to not cover it, but I guess whenever I made the video, somebody convinced me to cover it, and I ran over to the blackboard, and I covered it. I think I might have some slides somewhere that cover it in more detail.
Oh,
I would look for those.
yeah, but the example you showed me is just, yeah, this is a little tricky to understand.
Yeah.
And sometimes maybe because I want to understand it because what if it was on the test?
Well, let me tell you something. I
Okay.
don't put anything on the test unless I've really got it covered.
I mean, what if I have to because I'm just a little predict it will be on the test. This is what I predict.
Right.
So that's why we have to know.
Right. Well, all this stuff we're going to cover later. Here's Aries big O stuff. Here's a little. Oh, here's that. You've seen that before. What's this slide? This slide is not proving it. It's just explaining it. It's just stating it. So what does this say?
It's just
this says if you're summing a bunch of terms, then one option is to take the number of terms times the biggest term, right? So here, right? So this is times the last term and do a theta of it.
Okay.
So this is true whenever the terms are increasing sufficiently slowly, right? And what about this example? Well, here they're increasing way too fast, right? So 1 plus 2 plus 4. Here's 1 plus 2 plus 4 plus 8. See, it keeps doubling. And you can see that the sum is always the biggest term times 2 minus 1, right?
Yeah.
So what does this add up to, right? It's dominated, and this one too. Here it keeps going up by a factor of r.
Yeah.
Right? So here's a proof of this example. Let's say s equals 1 plus 2 plus, s equals 1 plus r squared plus r cubed up to r to the n, right? How do I sum them? Well, a trick is multiply the whole thing by r, right? And this one term turns into an r, and this r term turns into an r squared, right? And this r to the n term turns into an r to the n plus 1, right? But I shifted them. Why? Because now you see that if we subtract, if we take this minus this, what do we get? We get the 1 minus this last guy, right? And so that then we can then solve. We can solve for s, right? The s factors out, and you get 1 minus r or an r minus 1, depending on if r is bigger than 1 or smaller than 1, right?
Yeah.
So what is this? When r is bigger than 1, right? This is dominant. Let's say r is just 5, right? Then r minus 1 is just the constant that we ignore, and we ignore this, and it's dominated by the biggest term, right? And that's what this says. And this is true whenever the terms are increasing quickly. And what about this? When r is less than 1, right? Then we're doing 1. We're doing, where did we go? We lost it. Sorry, guys.
But it's not increasing that quickly because the ratio, the r is just less than 1, so it's not increasing that quickly. So it's just
getting smaller and smaller.
Right. So here, let's keep going. Here. What is?
Sir.
Yeah.
Is it possible if you could post this, or like is it already there?
I'll show you where these slides are.
Okay.
Yeah. Is it in the math?
It's in the math section.
Yeah.
Right? This is 1 plus a half plus a quarter plus an eighth. Right?
Right.
So when r is less than 1, this term disappears, and we're big O. Right? Which is still the biggest term. right?
Right.
So here, what do we conclude is that it's dominated by the biggest term either way,
Uh-huh.
right? So now the reason I'm not covering this right where where we are is because I started years ago by covering all of this math, and we didn't get to the material that we care about. So instead, I included as we need it. So later, we're going to need a sum like this, and we will prove it when we get to it.
Okay.
Right? Now that we're sitting here, let's look at some other examples. Right? So here, what's 1 plus a half plus a third plus a fourth plus a fifth?
Yeah.
This is called the harmonic sum.
Uh-huh.
And what does it sum up to? So let's just do some examples. Here, if f is always 1, right, then what's the sum? The sum is n, right? It's the number of terms times the biggest term, right? So that's 1 times n is n, right?
Right.
But now, if f starts to shrink, then maybe it goes down from, oh, why does it keep doing that to me?
Mhm.
I hate that. I don't think
Yeah, it's kind of.
Oops. Okay, let's do this again. That's. All right.
Yeah.
Here we are. All right. So now you can imagine having f decrease so that the sum is smaller than n, right?
Right.
Square root of n is smaller than n. And you can imagine here, if you shrink really fast, if you shrink by 2 to the I, then the sum is 1, right? So what happened here, we're shrinking in between. We're not shrinking that fast, but we're not shrinking that slowly. So we want to know what the sum is. And it turns out that it's log n. And one way you can see that is group together the first term, the next 2, the next 4, the next 8, the next 16, right? And then if you look at a block, well, it's going to go from, say, 1/4, and you're going to have 4 terms. This goes from 1/8, and we have 8 terms. So each block adds up to approximately 1. It adds up somewhere between a half and 1. And then how many of these blocks do you have? Well, because it doubles each time, if we go out to n, then the number of blocks is log n.
Log n.
Right? And you might remember from calculus, what's the integral of 1 over I?
Log n.
You might remember that it's
Ln.
Right? There's log base 2. Right? And in fact, 1 plus 2 plus 3 plus 4, actually, here I bounded it between, with a factor of 2. But the actual answer is exactly ln n plus or minus 1. Right? So that's what that sum is. And then here we talk about approximating by integrating. And here we're saying if the function grows really fast, it's dominated by the biggest term, right? If it's more polynomial, like into the 10,000, right? Here's 1.0001 to the n. Well, that's still that's still exponential. So it still is dominated by the biggest term, right? Well, here's a really, really big polynomial into the 10,000. In this case, the sum will dominated by n times n to the 10,000, right? 10 to the 10,001, right? We go to the other extreme. Here, this is shrinking 1 over n is log n. And if you go anywhere smaller than that 1 over n, it's going to sum to a constant, right? Anywhere bigger than log n, anywhere bigger than 1 over n, it'll go to n times the number of terms. Log n times the number of terms. Anyway, that's more than we needed to know. Any questions?
Yeah, it's just a concept. It's about proof that y does sum like that.
Well, I tried to explain why the sums were like that.
So you already explained, and I think I got that.
All right, good. Here.
Because I have to learn math.
Yeah. So
I mean,
these,
you told me it's just about math.
It's all math. So if you come down here to relevant math, right? Then the time complexity slides I have, but none of these other videos do I have. The slides are all in I guess this one.
Maybe
right? And if you want even more math, you can see I used to teach more and more and more of it, right? So more math has so many slides. If you want to know lots and lots about this, you can look at more math. If you want to know a little bit about it, you can look at math. If you want to know what we need for this course, you just wait till we get to it. Right? So in the example, what do I need you to know for the so far, when you got up to this slide, what I need you to know is you need to know this sum, right?
Right.
And I just gave you a hint that this happens. Now, if you go over to the GCD example, then we'll do exponentials. Now, have we done